Hello and welcome to lesson 12.1 on composition of functions. So if you click this playlist, especially if you know anything about math, if you know anything about Algebra 2, you're probably wondering, composition of functions, but the Unit 12 playlist is titled Sequences and Series. What does this have to do with series? Nothing really, actually. So this year spring 2023, I don't know. We just never got to this topic. I don't know why. I don't know. We just didn't fit it in anywhere. But we have to talk about this. It's important. Really, we should have covered it at the beginning of the year, but we didn't. So we're going to talk about composition of functions and inverse functions. We have talked about inverse functions before. And usually composition goes with it, but we never talked about it. So whatever. Anyway, the rest of the Unit 12 playlist is about sequences and series. This video, however, is not. It's about composition of functions. So I am going to talk about this. It's not related to the rest of it, but this year, spring 2023, this is just where this lesson falls. Okay, so here we go. Definition of composite functions. So what I'd like to ask you to do here is maybe just pause the video and try your best to read that. If you really know how to read math, you probably can, but assuming you're one of my students, maybe not, because this is some weird looking stuff, right? The heck does any of this mean? Again, really, try to pause the video and read that. Okay, so assuming you've done that, let me go over it. So what are we talking about, right? Well, when we talk about composite functions or composition of functions, well, you know how you have like f of x, right? You always have f of x. Well, what happens if, let's say I have f of x and I have g of x, right? But I take g of x and I make it the input into f of x. So maybe it looks like f of g of x, right? What I'm sort of doing here is composing a new function where the input is another function, right? So it's a function of a function, right? And that's what composite functions are. So I am going to read this out loud to kind of introduce you to this mathematical language and how it's written. What I'd like you to know is this probably isn't that important unless you're going to really focus in on math, all right? This is for the people who are going to be future math majors. This is how mathematicians speak. This is how mathematicians write about math. And I wanted to introduce this language to you because I like it. I like it. This is the professional thing that we do, and this is the formal definition of these things rather than kind of watering it down and blah, blah, blah. So anyway, I'm going to say let f colon a arrow b. What the heck does that mean? Well, you could read all of this if you want to pause and read that, but I'm just going to read this out loud. It says, let f mapping a to b and g mapping b to c be two functions. Then the composition function of f and g, denoted by g composed with f, is defined as the function g composed with f maps a to c, given by g composed with f of x equals g of f of x for all x in A. That's how you read that out loud. There's a lot of weird symbols here, right? You don't see the word mapping here. You don't see the word composed here. What the heck is that upside down A, right? Well, this means for all. And so basically what this is saying is, and maybe I'll make a little picture here, right? Here I have the set A, right? So this is the set A. And here's the set B. And so I'm going to take things from the set of A and map them to set B. And that relationship between those elements is the function f. And the function g, if I have some other set here, I call it c, right? Make a better little circle here. Let's say I have this circle here. G takes elements from B and maps them to C. So that's G. So if I wanted to map elements from A to C, I could do G of f of x. Because if you think about it, right, the output of f of x is going to be things in B. I'm going to call it B1 to tell you that it's in the range or the set B, right? Because what G does is it takes things from B and then maps them to C. But if you do G of f of x, it takes elements from A because the input into f of x comes from A, but the end result output goes to the set C. Now, it's just big. You're confusing me. What the heck? And I say, don't think about it too hard. All it is a function of a function. All right? So maybe I'll put this in yellow here. All this means is a function. Oh, I hate that F. Hold on. A function of a function. That's it. All right? So really focus in on this idea here because it's probably going to be the most tangible thing, like the thing you kind of understand right off the bat. G of f of x means that f of x is an input into G. So, yeah. Okay, so let's move on. And by the way, this notation, maybe I'll talk about this for a second. Goff, I say goff x, right? G composed with f of x, right? G composed with f of x. You can just write that as G of f of x. And really, just write it like that, okay? Because if it's just two functions, it's not a big deal. Just write it like that. I actually don't care if you use this notation that much. I am going to use it in some problems so that you get used to seeing it. But just understand that that's all it means, is a f is a function that goes into G, okay? So just focus on that idea. You say, well, why do you show this? Well, why use this notation? Well, if you needed to do J of H of G of F of X, it looks prettier like this than it does that. That just looks messy, and I mean, look at those parentheses, right? It just looks like a mess. So that's kind of why this notation is here. But again, it's fine if you don't use all these language and words. I just want you to see it. That's it. I just want you to be exposed to it. Okay, so let's do some examples, all right? Let's compose some functions. So example 1, let f of x equal 2x minus 3 and g of x equal 1/2 x squared. So we want to write the function h of x, where h is defined to be the composition of g and f, yeah? So here's a quick thing to remember, okay? Because it's very important you understand what the input of a function means, right? So when you say g composed with f of x, right? All that means is g of f of x. That's it. Now I might ask you, okay, look, if g of x equals 1/2, I'm going to erase this in a second, but let's say g of x equals 1/2 x squared, right? Well, then what is g of 3? And hopefully, because you're in Algebra 2, you should say that this is 1/2 times 3 squared, right? The idea is wherever x is, you replace that x with 3, whatever the input was. And so, I get 9/2, but who cares? The idea that I want you to get at here is that whatever that x is, you replace that input. So if I say g of, let's say x minus 2, right? If my input is x minus 2 rather than x, well, what would this look like? It would look like 1/2 times x minus 2 squared. You see, because the input is x. So I'm changing the input away from x, and I'm making the input x minus 2. So don't worry about what symbol's in there. Whatever symbol's in there, if I say g of penguin, I'm going to make a penguin. Yeah? G of penguin. Add him a little flipper and some feet, right? G of penguin means 1/2. I'm going to draw a little penguin again. Squared. That is what that means, right? Whatever goes in that parentheses gets replaced. Do not think too hard about it. So I see so many students think, what's going on? I don't know what to do. Don't think so hard about it. It's just the input, okay? That's all it is. It's the input. Okay, so here we go. You know what? I'm going to keep that lovely drawing. I'm so glad I didn't erase that. We're going to take you, and maybe we'll resize you a little bit. I'll say, whoop. I'll resize it a little bit. Put it right there. Yeah. Okay, here we go. So what does this mean, right? G of f of x. Well, what is f of x? F of x is 2x minus 3. So when you say g of f of x, right, what you're really saying is g of 2x minus 3. That's what you're saying. But maybe, if this helps, because there's kind of two ways you could go about writing this. The first way I'm just going to continue with this idea, is you say, okay, the input is 2x minus 3, so it's 1/2 x squared, right? Is x squared, but it's not, the input's not x, the input is 2x minus 3, and then that's getting squared. What I prefer to do maybe is to say this. You say g of f of x, right? Well, the input is f of x, so then it's 1/2, and then whatever the input is, it's x, right? So it's f of x, and that's what's getting squared. And so now you've inserted f of x into the function g, and then now you can substitute the function f. Now, either way you do it, I don't care, it's fine. You can substitute f as the input, or you can actually put the input in and then substitute f. You say, Mr. Spade, you're going too fast. I say, rewind the video and play at 0.25 speed. Okay? 1/2 2x minus 3 squared. That's what that is. Okay? Whichever way you like. All right? Whatever way you like. I will go ahead and expand. This is 1/2 times, let's see, that's 4x squared minus 6, let's double that. It's 12x plus 9. Okay, so this comes out to, 1/2 times 4 is 2x squared minus 6x plus 9/2. Okay? So I write it like that. I say, I hate that rectangle, quadrilateral. I don't like that. I'm going to draw again. Come on. There we go. Beautiful. Okay. So let's do the other one. And I'm going to use that other notation that I did, right? So find h of x. And so you can say, right, you say therefore h of x, because that's what my function is, right? It's a new function, h. So let's find h of x if it's f composed with g. So fog of x, right? F composed with g of x just means f of g of x. And so maybe you can say, so I'll write it again differently, right? This is f of, what is g of x? Well, g of x is 1/2 x squared. You say, I don't see that because you scribbled it out, and I say it's right there. Yeah, right there, okay? And so that's my input. So my input says 2x minus 3, right? But it's not x. It's not x. It's 1/2 x squared. So it's 2 times 1/2 x squared minus 3. And so this is maybe why I prefer the other notation, because then you could see this is the same as saying 2 times g of x minus 3. So you see what I mean? It's the same thing. It's the same thing. Okay. And so then I'll just distribute the two, right? It's x squared minus 3, and we're done. That one was a little bit easier. And so this is composition of functions. You essentially are making a new function by composing with other functions. Yeah, that's cool. All right. So go to example 2. Okay, suppose f of 6 equals -2, and let g of x be defined to be 3/4 x cubed plus 5. We want to evaluate g of f of 6. Okay, that's what that means, right? So what is g of f of 6? Well, that is just g of f of 6. Yeah. Again, I don't care if you write it this way. I write it this way. Me, Mr. Spake, I write it this way. But you might see that on a test or a context or something. Maybe you're reading from a college textbook and they chose to use that. Be familiar with the notation. That way you don't get confused. Yeah. So anyway, okay. So it's g of f of 6, right? Well, what is f of 6? F of 6 is -2. So this is g of -2, right? Because that is what f of 6 is. F of 6 is -2, so I just replace f of 6 with -2. So then I say, okay, this is g of -2, is 3/4, not x cubed, but -2 cubed plus 5. Now, of course, -2 cubed, that's -8, right? So that's 3/4 times -8 plus 5. And if I compute that, what's it, -24 versus, so it's -6 plus 5, which equals 1. Okay? So I just say, therefore, or if you want to make a nice statement, g of f, g composed with f of 6 equals 1. That's my answer. What the? Can you just make a rectangle? Okay. There we go. Let's move to the next one. Now, the next one's a little kind of a little tricky. Don't get too confused. It says g of f of 3 equals 4.25. What is f of 3? So what is happening here, right? You got your A, you got your B, you got your C. I'm just explaining what's happening here. You're trying to find g of f of 3. So the 3 is coming from the set A, right? And 4.25, that's in the set C. So here's what's happening. 3 is getting mapped to some value in B, and that value in B is f of 3. Yeah, so whatever this number is f of 3. And then that number, whatever that output is, that's getting mapped from the set B to the set C, which is 4.25. So 3 is getting related to f of 3, and then f of 3 is getting mapped to 4.25. So the question is, what's that middle number, right? What is that? What's the output f of 3? Or in other words, what's the input into G that guarantees 4.25? Okay, so let's see. Well, here we go. Let's try this. So it says g of f of 3. Okay, blah, blah, blah. G composed with f of 3 means g of f of 3. Okay. So g, we said, and then, by the way, this equals 4.25. So we ask ourselves, well, what's f of 3? I don't know. That's the question, right? I need to figure out what f of 3 is. But I do know that f of 3 is the input into G. And so since G, if you get my laser pointer, G is this thing, 3/4 x cubed, right? So then this is 3/4 not x, but f of 3. That's the input. And that quantity is getting cubed and then plus 5, right? This equals 4.25. And now I need to just solve for f of 3. So kind of pretend like f of 3 is just your x. And that's all you're doing. You're solving for x. That's it. It's the unknown, right? So I'll subtract 5 from both sides. I'll get 3/4 f of 3 cubed equals 4.25 minus 5. But that just equals, what, -3/4? Because that's -0.75, right? So, Yeah, so negative 3/4 over here. Now, if I just divide both sides by 3/4, right? If you divide by 3/4, that will cancel, and then that will cancel, right? So I'm just going to do that. And I'll find that f of 3, quantity, cubed, that equals -1. As you divide by 3/4 by itself, you're right, you get that. So that means if I take the cube root of both sides, f of 3 equals the cube root of -1. And what is the cube root of -1? It's -1. So, say therefore, right? Therefore, f of 3 equals -1. There it is. And so again, so to go back to that visual, right? You had your set A, your set B, your set C. What was happening? Well, the input was originally 3, and that 3 got mapped to -1 now that we found, and that 1 is getting mapped to 4.25. That's what's happening. Okay? All right. I hope this is clear. All right. Next slide. Okay. From this next part is kind of some time to think about it, some like classwork time to explore, right? But since this is a video covering what we did in class, I'll just do it here. So given the functions f and g, we're going to write the composition functions, g of f of x and f of g of x. By the way, if you want to read this like I just did, g of f, I mean, that's fine. That's what that means, right? Technically, on a technicality, it means g composed with f of x, but whatever. Same thing. Literally, same thing by definition. Okay, so I didn't give the most space on this, but that's okay. Here's what we're going to do. We're going to find g composed with f of x. I'm going to make a little bar here. And we're also going to find f composed with g of x, right? Now, here's right now, and I'm going to switch to blue, okay? G of f of x, that's g of f of x. This is f of g of x. So here we go. I say g of f of x. Well, what is f of x? F of x is 2x minus 6. Yeah? And so you could just say, okay, well then it's 1/2 times x, but the input isn't x anymore. The input is 2x minus 6. So it's 1/2 times 2x minus 6 plus 3. Distribute the half, you get x minus 3 plus 3, which ends up being x. Okay? So looks like g of f of x ends up being equal to x. Well, that's kind of nice. Now let's look at the other one, f of g of x. So f of g of x, right? Well, what is g of x? G of x is 1/2 x plus 3. And so this is equal to, right, this equals, so then this equals f of, the input here is 1/2 x plus 3. So that goes here, yeah? And if you're not picking up on this, let me show you another way, okay? Maybe another way to help. It says f of g of x, right? So another way to write that is, think of g of x as that penguin, right? What is f of penguin? Well, f of penguin would be 2 penguin minus 6, because you just replace x with penguin, right? So if it's g of x instead of penguin, it's 2 times g of x minus 6. So that's another way to say 2 g of x minus 6. I'm just showing you two ways about writing it. So it's 2 times g of x of 6, but we know what g of x is. G of x is 1/2 x plus 3, and then minus 6. And so then that's, what is that, x plus 6 minus 6. Oh my goodness, that's also equal to x. Coincidence, maybe. Maybe coincidence. All right. So that's composition of G and F. Okay, so let's do the next one. Whoop. I hope this is enough space. Okay. Let's find G of f of x and f composed with G of x. This is okay. So again, this is G of f of x. So if you want to do it either way, right? G of f of x. Well, G of x is x cubed. So then that's f of x cubed plus 5. So that means so what is f of x, right? Right? This is something cubed plus 5. Well, f of x is cube root of x minus 5. Now what happens when you cube the cube root? You get x minus 5 plus 5 just comes out to x. Boom. Right? And so then I do the other one. And I'm going to use the other. I'm going to just keep flipping between notations, you know. So this is f of g of x. So I say, okay, so then this equals f of, what is g of x? G of x is x cubed plus 5. So then it's cube root of, the input is x cubed plus 5. Right? That's my input. Then minus 5. So x cubed plus 5 minus 5, well, that's just cube root of x cubed, because the 5's cancel. And that's just x. You say, why am I getting x for all my answers? Well, can you make an observation about f and g? Yes. Yes. Pause the video, think about it if you haven't got it. But let me show you something. Suppose, right, so f of x, right, f of x, that's y, right, equals cube root x minus 5. Hey, what happens? What happens if I swap x and y? And then let's say I cube both sides. Let's say I add 5. And so that's y. And if you're familiar with this process, y would we call the inverse function, right? F inverse. We found that f inverse is x cubed plus 5. But guess what x cubed plus 5 is? It's g of x. So we've made an observation here. G of x is f inverse of x. And the same is true the other way. F of x is the inverse of g. And so this is our observation. F is g inverse, and g is f inverse. Yeah? Because if you find the inverse function, you'll find that that's what the other one is. So this is the sort of observation we made in class. You say definition. Let's get some formal definition here. A function f is said to be invertible. Invertible, what does that mean? If there exists a function g such that f of g of x equals x and g of f of x equals x. That is to say, the composition of both functions, right? F of g of x and g of f of x, both of those yield the original input x. This function g is called the inverse of f. And so now I think we've finally come full circle. This is the real definition of an inverse function. It actually comes from composition of functions. So we've been hitting on this idea of, like, you know, finding an inverse function, blah, blah, blah. And I've taught you that it undoes it, right? You know, x cubed versus cube root x. Well, why are these inverses? Because cube root is the inverse operation on cube. True, but when they get really complicated, right? X cubed plus 5, or like 2x cubed plus 5. versus what's the inverse of that, right? Well, let's see, it'd be like x minus 5 over 2, x minus 5 over 2 cube root. Those are actually inverse functions. But how do you know they're inverse functions? Because if you compose this function with this function, you get the original output, which is the idea that both functions unravel each other. They undo, they inverse all the other operations the other one has, and it yields the original output. In other words, if you find that the composition f of g of x and the composition g of f of x are equal, and they're both equal to the input x, then f and g are inverses of one another. And this is a way to verify inverses. So you might see a few examples in class or on your homework where it says, verify whether these two functions are inverses. If they match this property, I'm going to put a yellow star on this. If this holds, if this is true, then yes, they're inverses of each other. If it is not true, they are not inverses of each other. Okay. Now we're almost done with this, and we need to talk about restricting domain. And as your teacher, this is the one thing this year I'm a little frustrated with myself that I didn't spend more time on this and that we're kind of rushing this at the end. I am very happy to get on to series and sequences. I'm thrilled to do that. But I am a little sad, a little disappointed that I just didn't find time this year to really talk about restricting the domain. This is going to be an incredibly, and please listen to me, this is going to be so incredibly important in pre-calculus and calculus too, but specifically pre-calc, because that's where you're going to really deal with this skill. That's where you're really going to develop it, is understanding what the heck restricting domain means, why we have to do it, and how it works with inverse functions. Because the thing is, we're just talking about parabolas right now, really. We're talking about parabolas, we're talking about cubics, right? We're talking about logarithms, right? But in pre-cal, you're going to talk about much more complicated functions like sine waves and secant and all sorts of stuff, all right? And it's going to get really, really important to pay attention to function inverses in pre-cal. So I'll tell you this, the better you try and more effort you put into understanding this today, the better you're going to do in pre-cal and the easier it's going to feel, because you're going to do this exact same topic in pre-cal, but it's going to be with more complicated functions. And if you don't understand this idea, if you go to a context with more complicated functions, it'll be kind of hard to follow. Okay, sorry, I know, I'm yammering a bunch of stuff. Let me actually talk about what's going on. So, I don't think we've talked about one-to-oneness. So a function f is said to be one-to-one if each input has a unique output. That is, what does unique mean in math? Well, in math, unique means only one. So each output is paired with exactly one input. Okay? Now I want you to think about this, all right? It's kind of the opposite idea of what makes a function, right? Because in Algebra 1, here's what we tell you, right? If I have an input, let's say 2, right, and f maps to 5, then that is the only mapping that can happen with the input 2. If you say that 2 also maps to a different value, like, 7, right, then f is not a function. And, you try to understand that a little bit, but in Algebra 1, we essentially just come down to the idea that, right, if I have a graph like this, and I draw a vertical line, then because this vertical line intersects at multiple outputs, right? This y value, there's 3 y values that all share the exact same x value, right? They're all on this x value. So one input mapped to multiple outputs, functions can't do that. It's against their definition, right? But we have said it's fine if you have the opposite happen, right? So I'm going to erase all this. If I say that I have 2 and I have 3, and let's say I have the output 5 over here, if 2 maps to 5 and 3 maps to 5, that's okay because this can happen, right? Here's an example. If f of x equals x squared, well, what's f of 2? Well, that's 2 squared, which is 4. Well, what's f of negative 2? It's negative 2 squared, which is also positive 4. So what this is doing is basically saying here's 2, here's negative 2, and both are mapping to positive 4. And that's okay. It's still a function. But what 1-to-1 means is that this can't happen. This function, x squared, is not 1-to-1 because you have 2 inputs matching to the same output. What 1-to-1 means is each input has a unique output. So 2, if it maps to 4, then nothing else can map to 4. It's still a function if it does, but it's not called 1-to-1. And I hope you understand this idea of 1-to-1 means every single element is matched one time. There's no multiple pairs, okay? Okay, I hope I've explained this well to understand, because it can be a little confusing. Okay. So anyway, continuing on. In general, a function is invertible only if it is 1-to-1. So, in other words, if your function is not 1-to-1, it doesn't have an inverse. So, a function f does not have an inverse unless it is 1-to-1. It has to be. If it isn't 1-to-1, it doesn't have an inverse. You say, okay, I've got it, Mr. Spake. You can stop repeating it. I say, you have to understand this, because when you get to pre-cal, you're going to deal with these guys, and those aren't 1-to-1. And so we got to deal with it somehow. How do we deal with it? Well, you can quickly determine whether a function is 1-to-1 by using what's known as the horizontal line test. What is that? It's the same thing as the vertical line test, but just for horizontal. And rather than telling you whether f is a function, it basically tells you, right, the horizontal line test, what does it tell you? It tells you if f inverse is possible. Because if you draw a function, let's say I have a quadratic here, right? I draw a horizontal line through it, it hits more than once. Because it hits more than once, f inverse is not possible because it's not 1-to-1, so it doesn't have an inverse, okay? Unless, and this is the important part, star. If a function is not 1-to-1, sometimes you can make it 1-to-1 if you choose to restrict the domain. So, what the heck does that mean, right? I just showed you that this parabola is not 1-to-1. However, parabolas are symmetrical about this, right? And we do know that x squared versus square root x are inverse functions. We did explore this towards the beginning of the semester when we talked about radical functions. But what's missing on the square root function? The bottom half, right? I don't have that bottom half. That's because that wouldn't be a function, right? But this isn't the exact inverse of this. You have to change the original first. So what you have to do is actually this hump here, this shape, only comes from one of these legs. Which leg does it come from? Well, it's the positive leg. So what you have to do is restrict the parabola so it's just the right leg. And now this and this are inverses. Yeah? But what you've done is you said, okay, yes, it's the function x squared, but only for a particular domain, only for a particular interval, not for all real numbers. Okay, so let's look at an example. I hope you're with me. It's probably better in class. This is so insanely important for pre-cal. I can't even stress. It's like one of the hardest, like students will tell you it's one of the hardest things is inverse trig. Inverse trig. It's one of the most tricky mental mind games you have to play as a first-time student in trig. I mean, I'm good with it now because I've done it for years, right? But as a first-time student, that really got me. So don't worry. It's okay. You'll get it with time. You will. Or maybe you just already got it. I don't know. Let's say, given the quadratic function x squared plus 6x plus 10, let's give a restriction on the domain and then find that corresponding inverse function. So here's a quick word. I know that it's a quadratic, so I know it makes a parabola, right? Well, a parabola fails the horizontal line test, but if I graph the right leg, it passes it. If I graph the left leg, it also passes it. So really, you actually have two choices here. If you choose an x value at the vertex, you could say it's more than that, or you could say it's less than that. And it doesn't actually matter which one you choose. I'm going to stick with the positive result just because, but I want you to know that the negative result is just as valid because both pieces of the graph have an inverse. Okay, so how do we do this? Well, I showed you visually that you need to restrict the domain for a parabola using the vertex. Do you know what the vertex of this is? I ask, like a Dora Explorer episode, right? With the blue arrow pointing. Do you know what the vertex of this is? Where is it? I'm waiting. Okay, so how do we find that, right? How do we find the vertex of this? Well, we just got done with conics, didn't we? How do you find vertex form of a parabola? You say x squared plus 6x plus blank plus 10. And you can either add something to the left side or you can simultaneously subtract that same number from the right side, which is usually what we do for, or usually how I do it when I'm just dealing with a function like this. We're going to complete the square. So now, by now that you've been doing it, you know, take the big I, divide it by 2, then square it. 6 over 2 is 3, squared is 9. So adding 9 helps me complete the square on x squared plus 6x. But of course, if I add 9, I need to simultaneously subtract 9 on that same side. You could also think of it as f of x plus 9 over here and then not deal with this. But you're going to end up moving that anyway, so I just subtract it, okay? So this should now be factorable as x plus 3 squared, and then 10 minus 9 is 1. And so now you've found vertex form. So to give a quick sketch, your parabola is 1, 2, 3 over here, up 1. Your parabola looks like this. And so you need to choose a domain restriction. So if x is greater than or equal to 3, that's the right leg of the parabola. If x is less than or equal to 3, sorry, negative 3, then that would be the left leg of the parabola. So it's actually up to you to choose which leg you want. I'm going to choose the right leg. So choose x is greater than 3 as the domain restriction. Now let's find the inverse function f inverse. So you know that f of x equals x, what was it, plus 3 squared plus 1. How do you find f inverse? Well, you swap x and y, and then you solve for y. This is x minus 1 equals y plus 3 squared, and then I need to take the square root, right? So square root of x minus, sorry, not 3, 1 equals y plus 3. The question is it positive root or is it negative root? And how exactly do you know? Well, you chose the right leg, so it's the positive one, okay? It's not the negative one, so we're going to scratch that out, okay? And then I'll take my arrow up here, boop, and so square root x minus 1 equals y plus 3, so then y equals square root x minus 1 minus 3. Therefore, the f inverse function of x is x minus 1 minus 3. And that is your inverse function. We did do this a little bit in that unit, but it wasn't a major focus, and I told you not to worry about it at the time. Well, now we need to worry about it, okay? Okay. Whew, I think that was a long video, but it's good stuff. It's really, really great stuff, and we're stuffing kind of a lot in this. I probably would have taken more like 2 days on this normally. It just didn't work out that way this year, but that's okay. It's fine. It's okay. No problemo. And there you go. And by the way, I do want to show you. I'm going to actually open up Desmos here. Let's see, x squared plus 6x plus 10. So, oh my gosh, where's Desmos? Hello. So it was, our function was x plus 3 squared plus 1, right? That was our parabola. And if I graph, it was square root x minus 1 minus 3, right? You see it's that leg, right? Well, you haven't put a domain restriction on the red yet. So what you want to do, I'm going to put, is there a space bar on this thing? Hello? Oh, yikes. It's not like a key. Hey, I have a keyboard. Hold on. Let's do that. There we go. Now I can type blah, 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 blah. Okay. So x plus 3 plus 1, right? If I put a little bracket here and I say x is greater than or equal to 3, sorry, not 3, sorry. It's not at that, it's at negative 3. There it is. And those are inverse functions. And actually, one last little thing before I end the video. Inverse functions are symmetrical around the line y equals x. Meaning, if I type y equals x here, oh, hello? Y equals x. Think of y equals x as a sort of mirror, right? Orient yourself in such a way. Reflect that piece of the parabola over that line. That's the inverse function. And this is true for all inverse functions. So you can actually visually see when something's an inverse or not. Because notice if I make this less than or equal to 3, if I were to reflect the image of the red line over, I would not get the image of that blue line. However, remember how we talked about plus or minus the square root? This is the positive square root. If I put it the negative, now it is the mirror image over that line. So you can see how, the domain restriction kind of helps you figure out, what is. And remember when we talked about e to the x, we said, well, what's the inverse function to e to the x? Well, it's log base e, right? But we call log base e natural log of x. And ta-da! You can see it there, right? They're directly mirrored over this graph. You could do this for all of them. I really like cube root. So cube root x versus x cubed. See how they're mirrored, right? Perfectly across that y equals x line. So this is a way to tell whether functions are inverses graphically, whether they meet this condition. And so see, and just to, last thing before the video, if you look at sine x, this is the function you'll be talking about in pre-cal. This is a sinusoidal function. Flip that across the line y equals x. Right, y, oh my gosh, why won't I type? Y, okay, my keyboard is not, okay, y equals x, right? What does that look like? Well, there is actually a way to do sine inverse of x. But look, only a piece of it is graphed. Only a itty bitty teeny piece, right? And I think, if my memory serves me right, this interval is pi over 2, like so. And so now you can see that those pieces, if you restrict the domain of sine, you get this as well. Sorry, I'm diving a little bit too deep into pre-cal now, but I wanted to show you this is going to be a major thing, very big. So just try to remember that. So anyway, I hope you enjoyed the video. I know it's kind of long, but I hope it's interesting, useful, and helpful and all that business. And yeah, I'll catch you in the next one when we start series and sequences, which is totally unrelated to this. So there you go.